Welcome back to the NeuroBytes video experiment series. Previously, you have investigated touch sensing in the peripheral nervous system, interneuron processing of that sensation, as well as memory formation in the central nervous system, and now you'll have a chance to experiment with how motor neurons produce output back to the peripheral nervous system and muscles. Your NeuroBytes Motor Neuron simulators don't control real muscles, but they can control the movement of motors that simulate muscles. Let's get started. Each of your motor neurons has 3 dendrite inputs and 2 axon terminal outputs. Unlike the interneurons you've experimented with previously, all 3 dendrite inputs have the same weighting, which means that they all respond identically to incoming signals. Building a simple circuit, including the motor neurons and motors, is the best way to explore how movement is added to your neural circuits. So let's do that now. We'll be using a touch sensor and interneuron to produce input for the motor neurons, so connect them up as shown here, using a short dendrite on the interneuron. Again, the green power button icon represents your battery pack and cable, so those should be plugged in whenever you see that icon. Your motor neuron simulators can work with both excitatory and inhibitory input, so connect 2 motor neurons as shown here. Excitatory input into motor neurons leads to depolarization and action potential firing, which you've seen before. Inhibitory input into your motor neuron simulators produces unique behavior, which you'll explore shortly. Finally, connect 1 motor to each of the motor neurons. Either axon terminal output is fine. Give the switch a click on your touch sensory neuron. What you should see is that the touch sensory neuron and interneuron fire action potentials, as you would expect. The motor neuron excited by the interneuron should flash bright white, indicating an action potential, and your motor shaft should spin clockwise. The motor neuron inhibited by the interneuron should flash dark blue, and that motor shaft should spin counterclockwise. In the real nervous system, inhibitory inputs do not cause motor neurons to produce muscle contraction. Inhibition reduces motor neuron membrane potential, just like in other real neurons. However, this opposite motor behavior will be valuable in the future when you are using 2 motors to rotate simulated bones around a joint. In the knee-jerk reflex, for instance, a sensory neuron leads to excitation of the motor neuron innervating the quadriceps muscles, while an interneuron in the spinal cord inhibits the motor neuron innervating the hamstring muscles, allowing the leg to extend when a physician taps your patellar tendon. Normal movement of joints requires this coordination of excitation and inhibition of opposite muscle groups. This short introduction to NeuroBytes Motor Neuron simulators allowed you to experiment with how your nervous system detects the environment, processes that signal, and then produces a physical output. This is the basis for everything that your nervous system does, and will allow you to come up with more detailed simulations and experiments of your own. Want to share what you've built with your NeuroBytes? Visit us at www.neurotinker.com and show us your circuits.